But yeah, so a lot of things are built on Chromium. Chromium is like the underlying Chrome thing.
Mm.
Um, and so a lot of stuff is built by that. But yeah, hello to
Yeah, good
anybody.
point. I could have gone to
Don't
Chromium instead. But I like Firefox though. It took a few hours of tweaking, but it's working pretty well.
Yeah, I don't. I've got Brave on most of my other machines. I was using Brave for a
Nice.
while, and then there's
Yeah.
that whole BAT token, basic attention token, or whatever it
Oh, right.
is, like
Yeah.
just a shitcoin for like web browsing. But what I
Mm-hmm.
do, what I do is I was already using Gemini, which Brave has like a connection with Gemini, and so I already had a Gemini account from before, and so I was like, okay, whatever, like I'll just link my browser to Gemini, and so I've accumulated all these like BAT tokens, and then once I get like $15 worth, which it takes like 3 months to do, um, I sell the BAT and I buy BTC and then I withdraw it.
Okay. Yeah. Free,
So
free, free Satoshis.
free
Can't.
sats, man.
Yeah.
I paid my property tax today with my Fold card, um, to get sats back, and I got like, you know, 3,000 sats back just for paying my property taxes. And
Beautiful.
it wasn't an expensive amount or anything, but it was still like, wow.
Free money and yeah. If you think like how much miners will be fighting, yeah, will be competing like to get in
That
like
many
20
sats?
years, right? Yeah,
Yeah. Yeah.
the the block. What's the word?
Block reward or not
Block reward.
the
Yeah,
subs it's a sub block reward consists of the subsidy and the
transaction
or is it
fees.
right. That's what it is.
Yeah, so yeah, it's gonna go come down fast. It feels slow in the bear market, but it is fast. Look, zooming out.
It yeah, it really does. It's great. It's crazy to think about that because it's like where are we going to be in 2024? Like 2024 is the next halving. And so I
Hmm.
think about that and I'm just like it literally cuts in, especially with all the exchanges blowing out and people taking all their coin off of like I've had two people today say, "Hey man, like what should I do to get, get my coin off of the exchange?" And I'm like, "Go get a cold
Yeah.
card, go download, this mobile app, blah blah blah." But yeah, and then today Fidelity is, which I don't know,
Hmm.
this is probably a slightly tack on Bitcoin, but Fidelity is offering Bitcoin for their customers now. And so
Like for retail, right? If you have like a Fidelity in your app,
I
you can
believe
probably buy
so.
BTC. Yeah.
I believe so. I haven't looked into it deeply yet, but I believe so. And I think it's just more paper Bitcoin, honestly. Like
Hmm.
what a lot of these things have been. Um, but yeah, let's talk about. Let's see. Let's review. Do you want to run us through a review real quick? What have we covered so far?
So we went through chapter three, which is our finite fields.
Chapter what? Three? No,
Chapter
one.
one, right?
Yeah.
I don't know. We had the same confusion last a couple weeks ago, right? Thinking. Anyway, chapter one was chapter three. No, that's chapter one. Yeah. Chapter one, finite fields.
What's a finite field?
Uh, kind of a finite field.
I know we use modular arithmetic for to define a finite field. And that's because we basically, whenever we're doing addition, any arithmetic, addition, subtraction, multiplication, division, which division is like super weird with like exponential shit,
Hmm.
we modulo the prime, which is the what's the name for the prime of the finite field?
The order.
The order. Yes, yes.
Hmm.
We modulo by the order, um, of the finite field when adding, subtracting, multiplying, dividing, exponenting.
Hmm.
Okay. Yeah, that's it sounds like so little. I was like expecting to talk about a lot more, but yeah, that's what we did.
Yeah, and finite fields are it's where the math starts to becoming more. I mean, there are many math fields where it happens, but it's more abstract. So we're calling them finite field addition or adding field elements one to the other, right? That's when we do finite field addition. We're adding two field elements
Yeah,
to arrive at a third field element.
and there's
But
some
it's not regular addition. It's a finite field addition, which is
yeah.
it shares some uh, elements with regular math, but it's not regular addition.
Well, what it was it's it's defined with the properties. So
Mm-hmm.
it's closed. It
Yeah.
has an additive identity, which means it's just an element plus zero. An element times one is a multiplicative identity. Um, and this first one, this closed property where it's like a plus b and a times b, we are able to obtain that because of the modulo. Because when we modulo by a prime, you're guaranteed to have an answer that is uh, either one less than that number or down to zero, right?
Mm-hmm. So it's always going to be inside the field.
Yeah, it's the yeah, it's closed.
It's close.
Additive inverse, um, multiplicative inverse. That whole theorem thing that I don't think I didn't quite grasp, like the
Mm-hmm.
whatever equals one. Um, but okay, cool.
Yeah. And then on chapter 2, we went through elliptic curves.
Yes, and the and now I saw, actually I had sent it to you. There was um, the picture on Bitcoin Review podcast. But the picture,
Hmm.
like the picture in the center, is that the elliptic curve signature. Like that's the elliptic curve of Bitcoin of the.
And
Did you not see that one?
uh, it's funny. You sent me the picture of the whole podcast, and I was going to ask you, so cool. Was this a good podcast you're recommending? I want to check it out. A
Yeah.
good episode. But then you sent me the zoom in, and now I realized it's a crop from the actual screenshot.
It is. Yes, it is.
Oh, and they used the. We were just talking about it, right? They used the SECK P256 curve.
Yeah, I don't know. That sounds right. Yeah, here's
Oh, nice.
you can see it right there. It's
CCPK1.
can't get a bigger picture. It won't let me get a bigger picture.
SECP 256K1. Okay,
Two
that's it.
256K1.
Yeah.
Okay. But yeah,
So it will be.
that curve was it's in the Bitcoin Review like logo, and I never noticed it before. I imagine that you probably didn't. If even if you
Nope.
did, you didn't know what it was, just like me. Yeah, there it
We
is.
were just talking that we're gonna start seeing this everywhere.
Mm-hmm. Well, and then we
Yeah,
started
very good.
talking about the formula, the actual that makes that actual um, curve, which is y squared equals x to the third plus 7,
Mm-hmm.
right? Is that?
That is, yeah.
And that's just based on the curves themselves. Oh, here it is. Yeah, y squared equals x to the third plus 7 is the SECP 256K1. Um, because you can put in other like a and b's into the formula
To define different curves.
to find it. Yeah. Yep.
And But in the case of Bitcoin, we're only using this specific curve, which is A equals 0, B equals 7.
We didn't get into why yet, right? I wonder. I'm sure there's a reason why we use this specific curve, but
Good question. Yeah.
yeah, I don't think we've gotten into it yet. It looks like we got to coding the constructor for a point.
Mhm.
Um, it looks like we also implemented equals for the point. Yep, and we did the thing. Um, pardon
Let's see what SCCP stands for.
What does it stand for?
Yeah,
Oh, I don't know.
ECP, elliptic curve, right? ECP, parameter, I don't know.
Yeah, I don't know. Refers to the parameters of the elliptic curve.
2, 4, 1.
I don't. Yeah, I have no idea.
Elliptic curve, no, domain parameters. Yeah, well, yeah, we'll figure it out.
This might be too deep.
Oh, I was just looking at this one. Yeah,
Were you looking at this one?
yeah, same document.
Oh man. I'm sure there's some mathematical like reason behind it. Hmm. But anyway, we're programming Bitcoin. Let's do this.
Okay, SCC. It's not the SEC that we know, but it is Standards for Efficient Cryptography.
Oh, and what's
So it's
the
not elliptic curve. Then
standards?
the P, I don't know what that is. But on that same article on bitcoin.it,
Mm-hmm.
it's saying there. Okay, we have 3 letters. We'll get the remaining.
The K1. What's the P
The
stand
P.
for then?
Question.
There's some big brain math out there. Oh, SCP-256K1 has characteristic P.
I found that one as well. Right?
Uh, okay. It's out there. We need to put it out on Twitter. Somebody will know the answer.
Let's do that.
Or not. Um. Oh yeah, and you had given didn't didn't you give the code for determining if the point was on a curve or not? I thought you had.
I think so.
It was in Python though. Oh, I need to give you a live share.
All right. Yeah, let me get the link.
Let's see here. Well, there's our chat. Uh-oh.
Oh, look at that. It's interface. Okay, chat.
Should work.
It worked, okay. Open in Visual Studio Code, allow. Open. Okay, coming in.
Yeah, no worries. Let me know when you're connected, and then we can. I mean, the next thing we have to do is point addition, and that's I know we started talking about it, but it was a little late last time we were streaming. So
Hmm.
we sort of paused for a little bit. um, okay. And this has to do with the intersection. Oh, and there was something. Oh, yeah, we were talking about like why certain lines like through the top wouldn't be able to work for this, and it's because the points were not on the curve. Like you have to have 2 points to do addition. Both points have to be on on the curve.
Hmm.
So
So you mean, and then for that we had to actually check if the points are on the curve.
right,
Confirm.
right. Okay, 2 points to find a line. So for any 2 points. So let's think about this for a second. So we have 2 points, and we'll do public function add. Even though, oh no, we should do like we did the field element. We should implement add for it so that way we can use the symbols.
Hmm.
Oh, might be overdoing it with. Brought up Twitch. I think it was killing my PC. Anyway, we need to implement add. We give it self. We have an other. Now we can implement this thing. So you were saying we need to check if it's on the curve, right?
Yeah, I think anytime you're instantiating a point element, you should check if it is in the curve, which is through this equation, right? Yeah.
Yeah, so I think the easiest way to check that though would be just to make sure that A and B are the same, right? Because X and Y should be different since they're the XY coordinates. But A and B should be the same if it's on the same curve. So let's check that first.
Hmm.
Self.b.
Yeah, and you're using the double pipe for or, right?
Right. Yeah. So if either of those
And
are not the same, then we need to
it
panic.
invalidates it.
Panic.
Panic. Point. Points are not in the same curve, yeah.
I don't know if that's exactly the right error message, but it's good enough.
Yeah.
Okay. And so then, man, I'm not sure how we go from A to B to C. So we have to draw a line.
Hmm.
So there's some linear equation that we're going to need to reference to create that line. And then
that's where it got like wild. And that's where the math, like if you just keep scrolling down, he goes through the math. The
yeah,
math and it's insane. So that's where I was like, no, I'll just trust and not verify.
identity commutative associative invertibility. Okay. There's a 0. Okay. So some point
Mm-hmm.
I can be added to A, results in A. Oh, that's the point infinity. We looked this up, remember? The
Mm-hmm.
uh there's an infinity concept in Rust.
Oh, right. But you actually do have infinity in Rust.
I believe we do. Yeah, standard. So float 64. So I think actually then I think these XY coordinates should not be um, I
Mm.
size. I think they should be a float 64.
Mm-hmm.
And we'll see if this thing yells at us. It should. If it's wrong, but everything seems to be working still, so that's cool. Deprecating in future. Replace. Oh, it's just saying use something else instead. Okay. All right. So identity means there's a 0. So we have that in Rust. We have this infinity point. This is related to invertibility. A plus. Oh yeah. Okay. I remember reading this now. Um, where it's like basically if we add it to itself inverted, we just define it as infinity. Like the answer becomes the infinity point or whatever.
Mm-hmm. Yeah, then in Python it would be none.
Yeah. I remember reading that. Okay, a plus b equals b plus a. This one, I do remember this one being kind of weird. The associative.
Associativity, yeah. Which are all things we expect from regular math.
Right.
Mm. And that's why it can actually be called point addition and not point in something else.
Well, it's so a plus b, right? Third intersection is here. So this is the result of a plus b, and then we add that to c, which then intersects here, which becomes the final answer here. And then I think this shows the opposite of that, where we do
No, the final answer of a plus b added to c afterward would be that point next to b, the yellow point. Maybe,
right.
maybe that's where your mouse was. Yeah.
It was yeah, but it's the parentheses because you do a plus b first, and then you add c,
Mm-hmm.
and you get this point. But then you do the opposite. If you do b and c first, then it intersects here. Here's the answer, and you add a. There's the answer inverse, and it's the same. Like it's the same point.
Yeah. And the reason, yeah, he explains that the reason after adding a point that you actually flip it on the x-axis is exactly so these properties are constant and they actually happen. They actually can work.
Ah, okay. Well, I'm sure that has something to do with the fact that the elliptic curve is a mirror of itself, right? So you know that you have those same points on either side, just like the opposite y value.
Mm-hmm.
Because if it was some other kind of like graph line or whatever that was curvy and stuff, like you know, with an elliptical curve,
Okay.
it's a mirror, so you can have that reflection point. So that makes sense.
Yeah.
Um,
This point addition wouldn't be possible in other types of curves that aren't mirrored like this.
right. Yeah.
Yeah.
So let's put this comment.
So I remember, yeah, to yeah, he's building different cases, as you're seeing, like three different cases. So the add, the addition class is gonna have three different methods based on what the conditions of the points.
Yeah. So where are the points? Uh-oh. There we go. So yeah, the first one, where the points are a vertical line or using the identity point. Or point at, oh, the point at infinity, that's the point at infinity.
Mm-hmm.
All right, so this is a test here, so we should write this test. Do you want to write it? You should write it.
Yeah. Mm-hmm.
No, you want to have it within that. Yeah.
You duplicated a different text, and we're just gonna change
Yeah,
the variables. Okay.
you can, yeah, whatever. I was gonna use
That's
the.
better. I'm not good with the Rust syntax, so that's actually very convenient for me.
So it shouldn't. Well, one will hold on. We're gonna.
Yeah, the nuns are not what we're gonna use.
Well, we should copy this whole thing, right? Because we want to. You want to change the name of the test, so let's do that.
Mm-hmm.
And then I'll show you the syntax for like the infinity. But yeah, go ahead, change the name of that test function.
Mm-hmm. So this test as test.
Yeah, perfect. So this is
float 64.
yeah.
Bits.
Yep, and it has a this is like a static sort of constant on this type.
Mm.
So that's what, yeah, we would just be at the infinity point. And we can probably rename this infinity.
Or just I? Maybe just I.
So maybe. So I have strong opinions when it comes to that, where I don't like shortening things that you don't have to.
Mm. Yeah, good point. Otherwise, you come back and you have no clue.
Yeah, it used to be that like you only had so much space to write code, and like you couldn't go beyond like 80 lines, or there's like some weird like limits. But with modern everything, you don't have a limit. Like you could write an entire sentence as a variable name or a function
Mm.
or whatever. And so I'm a big fan of like writing what it is instead of just, because you also have tab complete, right? You have the ability to, once you start typing, it comes up and
Mm.
you know what I mean? Like, and it's quick.
So even if you're gonna have to type that multiple times,
Yeah.
it can be long, or you can just tab.
Yeah. Yeah.
You know, I was thinking I because of the identity point, but that's not even, yeah, it would be confusing because that's not I. I is not the point at infinity.
Well,
So
it is the
infinity
identity
is,
point, isn't it? Yeah.
no, the identity point.
Is a point at infinity.
Is it?
Yeah.
Oh, we'll call this point the point at infinity. Okay. So, but still, I like your point of being very thorough. You can even say that, yeah.
Yeah.
Yes. This.
But this becomes A plus B equals identity point. And then we don't need this second assertion.
Oh, okay.
Right, and that's essentially what he's
You can insert this, for example. A plus identity point equals B.
So I don't think
Oh,
that's
equals A. Sorry,
yes,
equals
yes.
A.
Yeah. Yeah, we can do that same
B. Oh, sorry.
Oh, you did it. All right, never mind.
With B, right?
Yeah.
Yes.
and then that should work. And this is that's basically this right here. Like we wrote this test right here.
Hmm. So now we have to to implement the class, implement the addition to the class.
But it says we're changing up the constructor initializer, the new function, whatever you want to call it. So it doesn't check the curve equation is satisfied when we have the point at infinity.
Okay.
Oh, okay. It's just all right. All right, you write it.
Okay. Where are we? Implement, add.
It'll be up
No,
on
it's
line
not
14.
14. Thanks. And it's before, right? We wanna.
Yeah, because otherwise the curve, yeah, it's not going to be on the curve. Well, it
If
should be on the curve.
self dot x is this rest equals. It's equals. It was float 64.
Yeah, F64, colon.
Infinity. Okay. Equals infinity or self dot x dot y. Higher.
I'm cleaning up as you go. You're good.
64. Infinity.
And then if it is, we're just what are we doing? We're returning.
Yeah, I think he just doesn't check anymore.
Yeah, we're returning.
And I guess the conclusion we get from this is that it doesn't matter what A and B is if it is the point at infinity. Because he's not checking if A and B are the same.
Well, the point at infinity, yeah, like A. Hold on, let me think about how to say this. Yeah, A and B is what defines the curve. Every curve has a single point of infinity. And so if it is just infinity, yeah, we don't care about the A and B because every curve will have that infinity point. So it doesn't matter, and we just return whatever the A and B is without checking it.
Yeah.
Because
I guess we are checking, like in the add function, the add method, we are checking if the A and B are valid.
Right. Yeah. Yep.
There are going to be other checkpoints.
Well, and I think that's the next section of code there, right? Like it's showing that we've got a if self.a is not equal to other.a, which we kind of flipped them, but whatever, and then we throw an error.
Yeah.
Oh, here it is. Okay, so this is the simple check next, like if x is F64. Another thing we can do, I think, is we can do this. We can import infinity, and then we don't have to qualify it with that F64 anymore.
Like define this will be a constant, not a variable.
It's not that it's a constant. It's we import infinity to be used by name without declaring like what crate it's part of. Right. So there's a standard crate, and then there's a submodule of that crate, which is the F64. I guess it's a module, not a crate. And then there's a constant in that module that is infinity. But when we import it completely, we don't have to do the F64 : stuff anymore. Like we were.
Okay.
Yeah. So this renamed it. Um, and yeah, you should start writing that other check just below mine.
The other check for.
So I just did number 3. So where self is x, or the self,
Okay.
that x is infinity.
Okay. So. Okay.
Boom.
We are returning self.
And then do a colon there because, yeah, we definitely want a colon there.
Okay.
Oh, and it looks like, yeah, you don't need parentheses. Oh, because it's the only expression. The reason we had parentheses up here is because there's 2 separate expressions.
Oh, interesting.
Because if you otherwise, there's kind of like an order of operations that the Boolean will evaluate to. So like if you don't have this on there, it gets weird.
Or.
Right? So like you want to, yeah, you want this to be coupled together.
Mm-hmm.
You understand Boolean logic and how that works, right?
Mm-hmm. Yes.
Okay, yeah. Oh, that was a pretty easy check. And then I think we should just to satisfy the compiler here. Oh, we need to add it. Never mind. So to satisfy the compiler, we're just going to return self at the end of this function. We'll go ahead and we'll clean that up later.
Mm-hmm.
But for right now, and that's just so we can run our tests. Let's go in here. Argument. Expected I size. Oh, we didn't change the. We changed this, but we did not update the method signature when we're creating.
Mm-hmm.
Oh, okay. Yeah, this is. So again, this is Rust basically yelling at us. And the lovely thing is, it says you might have meant to return this value, which is true, because we're just basically short-circuiting the check. Like we're short-circuiting this new method, and we just want to return right away because it's the point at infinity. Here's another lovely Rust compiler helping us out because we're dumb. It says no method named POW, and then it says, hey, but maybe you want to use this other one, POWF, which I don't know what that is. I'm assuming it's floating, which we have the. By the way, how's the video quality for you?
Much better.
Is it?
It is granulating tad, but not as much as on Discord.
Okay, perfect. We'll cut out the middle
I can read everything because when it was on Discord, like the edges of the code would get like very blurry.
Oh yeah. Okay.
No, this is good.
Good. Yeah. No, I just. Okay. Cool. So we've got raising to a power, so that's good. Or we could do an integer. So that doesn't work. So POWF is the name. And that's just because we're using our floating point. And then what's going on here? It doesn't like. Try using a float literal. Oh, it wants us to be more explicit that these are actual floats. What is this here? And this is where Rust gets, we'll call it fun. Because you get things like this where you can't multiply an I size by a float. So we'll have to. We basically need everything to become the same type. So I guess we should cast the eye sizes as a float. And I don't know what the trade-off for that would be.
Kind of related to what you were talking about a few minutes ago, that with the processing power that we have nowadays, you just default everything to the larger number. It should be okay, right?
Yeah. And I mean, I guess we could.
Which is float, I guess, if I'm correct.
Well, yeah, I think float. It's not necessarily the larger number. Um, like I think a float, because you have decimal points, you can't represent as big as a number as if you're
Mm-hmm.
using like a normal integer. But
Mm-hmm.
also, we're coding this for Bitcoin, and we need A to be 0 and we need B to be 7. So I'm actually going to use, oh man, what is, there's like there's an even smaller, it's like I8, I think. Yeah. So we can even
Mm.
use like I8, I think.
And it's gonna multiply, no problem with the floats.
No, I think we'll still have to cast it. But
Mm.
because an I8 is more restrictive to what the actual values are, right? So like this map, right? So I8 is a primitive type. Um, so like that's the minimum number is you can have negative 12,000 or negative 128. And then the maximum number is you can have a positive 127. And that's just because in 8 bits,
Mm-hmm.
you need 7 of those bits to represent the number, and then you need 1 bit to represent positive or negative.
Oh, okay.
But for our purposes, because we know that we're programming Bitcoin here, we can just use I8 here, and now, um, when we're going from an I8 to a float, we know that that I8 will always fit within a float. And I'm sure we could probably use like an I32 or one of the other I types, but like this is sort of like a premature optimization where it's like we know we'll use the smallest amount of memory possible to represent this number because we know this number is just going to be 0 and 7.
Hmm.
And there's probably some wazoo way, some shadowy supercoder out there that could like, there's some way
I4
to,
even.
to give the exact like, like make it a constant value or something like that.
Yeah, because with three bits seconds, you can draw 7, right? With 3 bits, you go into 8. So if there was an I4,
Yeah,
that could even work for you. In this case, for these two
that's true.
constants,
Yeah. We can do an I4.
which is, yeah, 1 bit for positive, negative, the other 3 for the actual number.
Yeah. You said you're a musician. You're pretty smart at this stuff for a musician.
Right? Yeah, I guess music is my math. It was always I always saw music as mathematics.
I've heard that before, and it's fascinating me. Maybe we need to explore that again one day. Um, but yeah, I mean, because sound is just sine waves, right? Like it's just
Hmm.
it's vibrations and frequencies.
Yeah, and like complex waves, one clashing with the other.
Oh, that's wild.
But it,
Because I used
but
to
it's
start,
cool.
I studied RF in the past, like
Mm.
radio frequencies. So I understand the whole like, certain frequencies come together and like they'll interact with each other. There's, the different mediums that you have waves going in and out of, like does different things to it as far as like diffraction and all that kind of stuff. And that's all applicable to sound too.
Yeah, just in a different order of magnitude of frequencies.
Huh. Well, I married an opera
Even
singer, so.
that's right. Even rhythm and pitch are just two different uh, manifestations of frequency. Like pitch is clear, like you have a wave that's vibrating at like 440 hertz, and that's an A note.
Yeah.
And from there, you create all the other frequencies. The rhythms are just that frequency, but much slower. So when you have a
Yeah.
112
Yeah.
and 20 BPM rhythm, that's 2 hertz, right? Or
Yeah.
no, wait,
Yeah. Yeah.
zero
Yeah.
point 0.5 hertz.
Huh.
Yeah, so it's all vibrations in the end.
Oh, we're living in a simulation.
I think 120 BPM is 2 hertz. It's 2 beats per second. Yeah. 60 BPM, 1 hertz. Exactly. 120. And so on.
That's so cool.
Yeah.
That's so cool. All
So
right,
so
so
there you're casting A, then you're just casting it momentarily as a float, just so it satisfies that equation.
right, and we know this is a safe operation to do, because an I8 will fit within a float 64, like guaranteed. Um,
The opposite could run into errors. That's the
right. Yeah, and I don't.
if you were to cast X as an I8, for
I
example.
wonder if the compiler would not let us do that.
Hmm.
No, it looks like it's letting us do that. It's just saying that we can't. Yeah, I mean, code will let you shoot yourself in the foot. But we'll pay attention to that. So that works though. I think we can compile now. Oh, another thing is we
Yeah.
don't need this POW anymore. It's gonna complain about that. So yeah, let's run these tests and see. Oh, what's going on here? Oh, okay. So it's just more of us not being explicit when we're passing in these values. So do you see what it's saying?
Expected float, found integer. Okay. And so on.
And then it gives you that, like, the Rust compiler is so beautiful because it gives you recommendations, and it just says, "Oh, we'll just use 1.0 instead of 1."
If you do that, that will solve it.
Right.
Like it gives you the solution.
Yeah. So
Nice.
you want to help me clean these bad boys up?
Yeah.
And then I think, yeah, so 5 and 7 should be fine.
They are I8s.
And then yeah, we got to change these. Cool.
And this one as well.
Yep. Ah,
Double dipping.
you're faster than me.
In
Um,
our identity point.
yeah, what's going on here? This doesn't like it. Oh, it's a bar. Okay. Yep. So this is the whole. Hold on, just a second.
Bless you.
Thank you. This is the whole Rust borrowing thing, right? And if we read this, we can understand kind of like what's going on. So it says it's moved, which means the ownership of A has moved, and if we look, it tells us. So the error itself is occurring on line 91, right? That's okay, cool.
Mm-hmm.
But then it says that it was moved on line 90 due to usage in an operator. And then if we look at 86, it's saying, hey, this variable is type point and it doesn't have this copy trait, which copy is, there's like these things in Rust, called traits that kind of allow you to inherit some functionality or some characteristics, by just adding the trait. And so we can try. I think we could probably just add copy. I think it'll be safe to add copy. And I'm gonna have to look. I think it's trait. Man, I'm gonna have to go look up the syntax for traits,
Mm-hmm.
because there's a special way, kind of like we annotated those tests down there, where we, um, had that. Where's the trait? Oh, there it is. Derive. That's what it's called. So we can derive different traits, which will kind of automagically do the thing for us. Which we can do clone and we can do copy. Um, again, clone sort of has to do with sort of like creating duplicates of the object or the values or the struct rather. But yeah, if we use copy, this cleans up our code down here, and it's trying to figure out a good way to explain it, but yeah, it
Yeah.
allows us to copy A, so that way it's not consumed when it's used, if that makes sense.
Does it relate to garbage collector or memory management or
So
something
yeah,
else?
it's memory management. There's no garbage collector in Rust. You are explicitly memoraging mem ma-
Mm, mm,
you
Memory managing.
you're managing the memory. Yes, thank you. Um, but the compiler is really smart in that it can infer a lot of things for you, right? So like these highlighted bits here where it says like this A is a point, like that's an inference, right? It knows it's a point because the function new on this type of point, or in this this new function returns a point, and so it can infer that. And that's a very simple inference. But in this case, what happened was this A plus B means that A and B, in normal cases, without that copy trait, are being consumed, and those variables cannot be referenced again. And it's a way that Rust prohibits. Well, it doesn't prohibit. It's a way that Rust stops you from referencing a point of memory that is no longer there, right? So without that copy trait, A plus, like once A adds to B, like it's gone. Like A and B are no longer considered valid variables to be referenced. Um,
Nice. Okay.
but because we implemented the copy trait on point, which is the type of A and B, then now we can it will the compiler automatically like knows it's like, oh, you're adding A and B here. Oh, but then right below it you're also adding A again, and below that you're adding B again, and like you're
Just
referencing. Yeah, so it automatically like copies itself. Like when it does the compiling, it says,
can I try something real quick? So I'm gonna comment out the derivation you had in
oh
the
yeah,
beginning. So then I think our A's and B's are gonna be, they should start throwing error again. So
mm-hmm.
yeah, here we are again, right? So say I did this. You know what I mean? Then I recreate A and B just momentarily.
Yep.
But this would, right? Because yeah, I'm telling it to recreate A and B again. Or not. Yeah.
Right, but you'd also have to do the identity point as well. Oops.
Okay.
Yeah, you'd have to do the identity point as well, because that's also a variable, right? Like that's also
Mm.
a variable that is which we'll call it.
That we need, yeah, not just A and B, but the identity point is also being consumed.
Yeah, and then that, I believe.
Yeah, I think it's complaining. So because B we're not really using it here,
Oh, this
and
is
A we're really not using it here.
well, it's not necessarily. It's complaining because we have the same variable reference on both sides of the uh, of the comparison. So it's
Oh, really?
A is being
Hmm.
consumed in this function, and so it
Oh,
cannot be
wow. Okay.
used as the opposite side. And so what you could actually do here is you could do let A clone equals A dot. Um, because we have not implemented clone, so we
Hmm.
cannot call the clone function. So if we go back up here and we add in that, we'll take out the copy function. But if we add in
Nice.
clone, now
Also, if you add A underscore, oh no, clone, you're using it as a method. Okay.
and now we can do. Let's see. Let's save that, and it's still complaining here, right? Like A is being moved. But if we use a
Hmm.
clone, now this is happy.
Nice.
But what we've
Okay.
done is we've just cloned that section of memory and just like re-added it. And I think that's kind of what copy might do behind the scenes. I don't know.
Automatically.
Yeah, automatically. Isn't that a great word?
It is.
So yeah, I don't know exactly. Copy might do a little bit more than that, but it
Hmm.
just saves you writing so much code, right? Like it's just all of this because
Yeah.
we would have to do the same thing down here for B. All of this is now just one line that we add on the top of our struct. Um,
Nice. Okay. Yeah, that's great. No,
yeah,
totally understand. But on the other hand, the default is max performance,
yeah. The default
right?
is we're not going to
Show
copy, we're
me.
not going to clone anything, um, and that's yeah. It's yeah. I don't know if it's a Rustism to clone things or not clone things. Like obviously
Mhm.
that's if you're going to improve, if you're trying to go improve memory management and performance, you're going to look for those types of function calls where you're cloning something that's a huge swath of memory, and then maybe you can manage that better, um, with some more
Mm.
elegant code, I guess.
In this, you can trace. You just get rid of that. Yeah, and then you can differentiate Rust from Python in this sense is that Python will have all the clones and copies and everything that makes the memory management easier, but then performance suffers greatly, like in comparison to Rust or C++ or other
Yeah, I mean, if
better
you're
performing
concerned about
languages.
yeah, if you're concerned about performance, then yes, like you're gonna have a lot more performance out of Rust, um, just at a
Mhm.
baseline, I think, in general. But also, I mean, Python and some of these other garbage collected languages allow you to really manage the memory. So like if you really wanted to be that like, memory efficient or what have you with Python, it's doable. There's
Mm.
actually a pretty interesting blog post that it was a few years back when I first started dabbling with Rust, but it was Discord that we're not using right now because we're using Keat.io. Go check it out. It's an alpha. It's super sweet, peer to peer. Get the decentralized middleman out of your life. Um, anyway, it was yeah, it was a blog post where Discord had some sort of like service that was running that was written in Go, which is a garbage collected language, and they kept getting these like spikes on the CPU. And it turns out that was the garbage collector, and it ran every time, no matter what. Like they had optimized this thing to use like just such a fine amount of memory, but it
Mhm.
still the garbage collector would still spike, and the garbage collector was actually using more CPU than the service itself that they had optimized out to Wazoo. Well, they rewrote
Mm.
it in Rust, and it was just flatline. And again, this was like years ago, so Go might have improved that, like adjusted or that tunability or adjustability of the garbage collector. Um,
Mhm.
but it's just one of the things that kind of stuck out to me as far as that goes. And then also you got to think about are you writing code that needs to be that efficient? And
Yeah.
usually with Python, like people, I feel like Python's a good like rapid development tool, so people are just grabbing it to just get stuff done.
And then when you achieve scale, then you end up having to switch.
Right, right.
Yeah.
Um,
Should we run our tests?
we should, yeah. That was a lot of talking to get to that point, but yeah. Uh oh, something failed. Test failed. What failed? Unused variable B. Okay, that's fine. But what failed? So there was a panicked assertion that A plus B does not equal the identity point. Is where it panicked. So in this first assertion, um, oh, they're not the inverse of each other. And we also didn't implement that feature yet. So we should do this, and then we should assume that will fail at line 93, but line 91 and 92 should pass, right? Because we're only checking
Hmm.
if ourself or other is infinity.
Oh, we don't have the rest of the implementation yet. Okay.
Right.
Mm-hmm.
And should we? Okay, so this is the identity point. So
Yeah, we might have some.
go ahead.
We might have some ambiguity with what is identity point with what is infinity with.
No, infinity
Or
is the
no,
identity point. So look, okay, so we at least passed these first two tests, like these two assertions, because
they passed. Okay.
yeah, because we panic at 93. So like
Hmm. Okay.
we're good right now.
Ah, you run it again just now.
I did,
Cool.
but we didn't handle the inverse property, right? That's what it's called? The
If
inverse.
A equals minus B, or if self A, yeah,
Yeah, we just
A is the name of the point and also the name of the coordinate, so that's a little confusing.
yeah.
Maybe we should do P1, P2.
Let's do it.
But if self P1, if self X of P1 equals the inverse of self X of P2, that should be the identity point, but we have to implement that still.
If say Say that again. No, that's the vertical line, right?
Mm-hmm. Yeah, so if it's the inverse, it should equal the identity point if you're adding the two.
So we could check that by adding together self x, other x, and if it's equal to 0, then we know it's
Yes.
vertical line, right?
Mm-hmm.
Okay, so wait, say so if
Yeah.
self x plus other x, equals to 0.
Yeah.
And then what do we do there? It doesn't.
What are we
We
doing?
return the identity point, right?
Yeah, the sum would be infinity. Yeah, we return the identity point.
So I think. Ooh, okay. So I think here's an opportunity for us to define a constant. So identity point.
It would be exercise number 3. Yeah, exactly where you are.
Okay. I guess we could do. I'm trying to think of like a quicker way to reference like the identity point of a specific point, but we'll have to new it up anyway.
Mm.
So if self.x plus other.x is equal to 0, then we need to return a point where, how are we define it? X, Y, A, and then B. So
X and Y would be infinite or infinity.
Right. And then it would just
On Rust, do you have to define the X, Y, A, B in different lines like you're doing? Or
no,
that's just the Rustism?
no, I forgot. I wasn't calling I wasn't creating a struct necessarily. I
Mm.
was I needed to call the new
Instantiate.
Yeah, I needed to call the new function, and I just forgot.
Self.a, self.b.
So what's going on here?
But even for the struct, as you have like over there, do you have to put it in separate lines, or that's just more industry
You
standard?
talking about here?
Mm-hmm.
So this, because this is a function within point, we can I don't know how to describe it. We can create that. I mean, I guess we could have. Hold on, let me check. I think we can maybe do this. Yeah, so I guess we can define it like that, where we're just returning a point. And I think that's because we're in an implementation for point, so we don't need to call like that initializer.
Okay.
So that's what I initially was doing. What I guess like what I was thinking of doing was this, where you return the. Which I guess I can't do that here. I don't know why. Huh.
No, either way.
All right. We'll use the
Yeah.
function.
Let me just show you how Jimmy solved it in the book. It's very similar, but he just thinks this is Python. So self x, other x are the same, but different y's. Then they have to be a vertical line because they're the same location in the x axis, different y's.
Yeah. Okay. We did this
That's
backward.
how
We did.
he.
We did this backward then. I think.
It's. I think it's effectively the same thing, right? It's just the approach, the angle is different.
Oh, I need to look at a graph.
I bookmarked the Desmos website. Super cool.
No. So self x would be the same as other x, and then self y plus other y equals 0.
Oh.
Right? To have a vertical line.
Oh, okay. Okay. Oh, yeah, good point. Good point.
Yeah, we I think yeah, we got that one. We were off on that one. And so
Like if
self
y
x,
is 1, y is minus 1 equals 0, and self x equals other x.
right. That's a vertical line. Wait, so why does he have the y is not equal to other y? Is
I
there
guess if you have 2 points on the same x position, they are going to be, the y's are going to be equal to 0
yeah.
because the equation is mirrored in the 0 axis, right?
Yeah,
The x axis.
I'm trying to think of why you wouldn't do that check to ensure that.
Because if self y equals other y, then you're adding the same point twice, which is a valid operation. It just wants to confirm that it's not 2 points in the same location.
That's yeah. Okay. So we should probably add that check in. But we get that check regardless because
Mm-hmm.
we're adding y. Like if yeah, because if y is 1 and we add it to an instance where y is 1 again, then that's not 0. So it'd have to be
Mm-hmm.
y would have to be 1 and -1 for 0 to be true.
I guess the only exception would be if y were 0, then y plus y equals 0, and it is the same point.
It's the same. Yeah.
What?
Oh, yeah.
So they're
But that
not
is the
different ways.
is that not the infinity point though? Is that why it's the infinity point? Because you add it to itself and it's itself forever and ever and ever?
Yeah, that's yeah.
But
So
I know
yeah,
what you're
so
saying, but
that
yeah, like that in that instance, it would be at the
that's what we're looking for. Yeah,
it would be at
yeah.
the infinity point.
Mm-hmm. Yes.
Handle case for 2 points. All right. Do we?
Additive inverses.
Did I go beyond where we're at? Where were we at? Handle
We
case
have
for 2 points are additive inverses.
yeah, this is the one that we just did. Right?
Yes, that is. Yes, you're right.
And now the second case is like regular addition, and that's where the I trusted. I didn't verify all the way
This
because the
next.
math
This.
gets really crazy. Yeah, I just implemented the equations that
Okay.
he gave us.
Well, let's come back to this because I do actually have to stop here shortly, a
Okay,
little sooner than usual.
no problem. Yeah, there is. I went like I calculated the slope. I did some practice doing that, but then on that square, like that section just gets so insane.
This here,
The
the deriving the point.
deriving, yeah, that one.
Okay.
Just
All
look
right.
at that. Look at those bad boys there.
Yeah, I'll have. Okay. See this.
Maybe yeah, if you spend some time with it and you.
Yeah, well, because I know there's like a lot. There's a formula for like a slope of a line, and
Mm-hmm.
there's ways to figure out if 2 points create that slope or vice versa type of thing. It's just been a while since high school.
Yeah, which is yeah, what he's doing there.
Yeah, yeah. Okay. Well, Pleb Lira, this was another awesome session.
Yeah,
Um,
it was.
I think we'll continue to keep that at IO. Uh, so, shout out to the random pleb paying attention to this chat or video at some point.
Shout
Um,
out.
I'm gonna try to get these on YouTube. So we have 3 videos now. This is our third recording or third streaming, and I've got the videos downloaded, and it's just a matter of sitting down and not having holidays with the in-laws. So
So maybe in January, right?
yeah, yeah,
When
maybe.
life starts again, because now, yeah,
Yeah.
it's so busy. Yeah, this was great, man. So I'll see you next Monday
I'll
for more programming Bitcoin.
see you next Monday.